recording computer. Okay, cool. We're officially recording. Hey guys, welcome to Rocket League Week 2. Today we're going to be talking about Open Rocket and how to design your rocket for the project. One little announcement I want to make to everybody watching the video later or watching live is that we have the objective and team signups open right now in the Discord. I sent the message like half an hour ago today. Make sure that you fill that out at your earliest convenience because I'd like to form teams next week. So having your forms, filled out will let us put you in a team. It will ask you if you have a team in mind. If you answer no, don't worry. We'll find you a team if you don't know people already. But if you do know people, then absolutely, there's a section where you can put their names down and we'll figure it out from there. Also about that, if you have not paid your dues yet, please do. If you have not paid your dues and we are forming teams, we may not put you in one because you need to be a paying member of the AIAA in order to participate in the project. If you guys pay and it's not in for us, you can message us and we'll figure it out, but do pay sooner rather than later so that you can get in the system. It's just on the AIAA UCF website. What's up? If we know a person. That's fine. Just so a question, like kind of private, but it's good for everybody if you don't mind. It's asking if you know someone but you don't know their name. Totally fine. Put their Discord name. You can put their real name and Discord name on the form. Because it does require that you put full name, Discord name, kind of like the first sign-up sheet. So whatever you have to refer to who they are, we can work with that. And if there's any troubles, you don't get put in the team you want, you can always talk to us and we could try to rearrange teams a little bit. So yeah, I think that's it when it comes to announcements beforehand. Now we're going to talk about Open Rocket. So what you see here is the window for Open Rocket. I know my face is kind of blocking some of the things up here. Actually, this is quite nice in a way. Anyways, so Open Rocket is how we design the actual rocket. So I'm going to go through each thing step by step, sort of following this PowerPoint. Let me go to the top again. But this PowerPoint here kind of goes through the process on how to design the rocket. I'm just going to be going through showing you actually how to do it. And if you follow my steps, you can always change it up based on how you want to design your rocket. But this is like the basic how-to. So let's get started. First, we start with this blank form here. Just a little synopsis of what's going on here. This top part here, these are all the parts that you can put in. And so you click and it'll put the part down here. This will show you your rocket, kind of like a side view of your rocket. Up here, it says rocket, that's just name. And let me see where stability. Okay, one thing that I want to point out to you guys. Yeah, I'm gonna have to move myself around a lot. That is, let's do this for now. Okay, so the way that this works is that down here, you'll see a few things. First, on the bottom left, apogee, super important. The apogee is the highest altitude that your rocket reaches during flight. We're gonna give you guys a particular apogee that you're going to aim for. This is for all challenges from altitude, payload, and lander. So this is how you'll know kind of how far your rocket's going to go. Of course, in the real world, the atmosphere has various pressures. There could be wind and all these different factors that can ultimately lead your rocket to not really reaching that exact apogee. But this is a pretty good estimation of where your rocket's going to end up. The next thing that is super important is this stability to the top right. Last week, we were talking about rocket stability. I was explaining to you guys how it works. And I told you that we like a stability between 2.0 to 2.5 caliber. This is what I'm talking about from last week. You want the number on the top right here to be from 2 to 2.5. If it is not, I'll show you guys here how to make the adjustments to make it more stable. Other than that, this is the really basic stuff that you need to know. So we can just get started. Oops, let me show my face again. Okay, so first we're going to put on the nose cone. So the way that it works, you look here, nose cone, put it down. So whenever you put a part on, it'll put it on the bottom and you'll see this window right up here. You guys see this window, right? This nose cone configuration, component name nose cone. Just want to make sure that you guys see my whole screen.
Yeah.
Okay, cool. Chat says yes. Heads up, I'm here. Oh, nice. Hey, Mark. Yeah, no, if you see that I missed anything, Mark, please interject and let me know, hey, you missed something. So you can go from there. All right, so after you put in your nose cone, there's going to be a bunch of different options. What's likely going to happen is you guys are going to be given a preset nose cone. The slides say to do an LOC PNC-300 from the database. So the way that you access all database parts is you look on the top right, select preset, click down from database. You're going to have all these options. What you can do is, you know, it's this very tiny box that says filter by text. If you kind of click and you hit LOC, you see how you don't see it up here, but if you click on this little box and you start typing, it'll show everything here. So we're looking for the LOC PNC-300, which is, oh, it should be 3.00, but still, it is this. Oh. So you hit the little checkbox, hit OK, and then it does not work. Oh, okay. Oh, okay, there. Sorry about that. It puts it here. You click. Hey, look at that. Your nose cone is now put to that preset. Once we give out the bill of materials, you guys will know exactly if this is the nose cone or if there's a different one they have to select. But I think the LOC PNC 3.00 is the one that we're using. Just a little thing, sometimes teams can design their own nose cones. If you were to 3D print it, you can basically make your own shape, whatever you want. The way that you would do that is if I go select preset again, it's already done that. Let me just quickly delete this nose cone and show you the different options. So here's how you make your own little nose cone. First, you can do shape. There's a bunch of different ones that you can kind of play around with, like conical is this little triangle shape. O-guide is kind of curved based on a particular formula, ellipsoid, like that. And you can play around with all these. You can play around with the length. For the base diameter, you want it to be 3 inches. Might be 3.1 or something. Basically, you want the diameter of the nose cone here to be the diameter of the body tube, or the outer diameter of the body tube, just so it like kind of sits nice and flush. Wall thickness, I forget what we set that to. Well, it will be based on the LOCPNC. So wall thickness 0.125 inches. Yeah, so you're going to want to do something like that. Actually, this is quite nice to work off. So just back to this. I'm really sorry for the mess. Nose cone length, play with it. Shape, play with it. Wall thickness 0.125. Cool. For component material, put plastic. I believe that should be. It's either plastic.
It should be polystyrene.
Oh, polystyrene. Oh, my bad. There you go, polystyrene. Basically, the way that you would do your nose cones custom is you would 3D print them. If you go to the TI lab, they have 3D printers, or if you know someone with a 3D printer, you can 3D print your nose cone. I've done it before for my level 1 rocket, and it worked. So you just make a SolidWorks mock-up of your nose cone, and then 3D print it. Another thing that you have to keep in mind is you need to click this shoulder. What the shoulder of the nose cone is, you imagine you have a nose cone, and then kind of under the bottom, there's like another little piece that fits into the rocket. And so that's how it secures the nose cone into the rocket. So if we add a nose cone shoulder, let's see here. So in essence, what you need the diameter to match the inner diameter of the body tube. So we put 3 inches. We could put a length. Ooh, let's see what a good length looks like. Uh-oh. Looks like my nose cone's base diameter is pretty small. There we go. It's going to look something like that. So you could put a length here. I forget what I put my length to. We'll check with the LOC preset later. And then thickness, you should add the 0.125 as well. Just to make sure it has the thickness. And you can kind of get the gist of how you make the nose cone. So for the LOC, it is 3.75 inches. So that's about the length of the shoulder that you want. But that's all stuff if you're making your nose cone. If you're not making a nose cone and just using one of ours, just use the preset, and it's just a lot easier to do this. I think that's all the parts that I need to talk about nose cones. Yeah. Does anyone have questions about nose cones before I move on to body tubes? Or cool. Yeah, I'll move on. All right, so we have a nose cone, but that is only one little piece of the rocket. Now we put in body tube. Where is it? It's right here. Pow, you add a body tube. So the way that the body tube is, you're going to want to use the LOC BT dash 3.00 from the database. This you want from the database for sure, because that is the nose or the nose cone, the body tubes that we give you. So you go LOC, precision BT, this one. Okay, go back, hit it. There you go. Okay, so now we can see, let me put my stuff away so we can see the whole body tube. So now the body tube is like this. So this is one long piece. If you are doing the payload challenge, leave your body tube like this. You will have just one big solid piece. If you're doing altitude or payload, not lander, you're gonna be splitting your body tube in half down the middle. So the way that you do that is you take this and change it to half, which is 17 inches, I believe, 34 divided by 2. And then you're going to go ahead, close this out, and you can look at the components that you've actually put into your rocket, hit body tube, Control C, click out, Control V, and you can see that you've made 2 little sections for the body tube. So now you have 2 halves of, one bigger body tube. And the way, when you do this, you're going to have to put something called a coupler. Basically, imagine you have 2 ends of your body tube, but they gotta kind of slide together somehow. So you actually put in this, a coupler, right here. So if we go to the, I've already done that, tube coupler, the TC-3.00 preset. So from database, TC, dash 3.0, there you go. It's still the LOC precision. Click OK. Alrighty, now what we want to do is you kind of have it, I did this really bad. What I should have done is I should have put it onto the top half of the body tube, but I accidentally put it onto the bottom. If you look here, we have our nose cone. This body tube is this one to the left, and this body tube is this one to the right. So if I click and then drag this up, I can put it into that body tube instead. And its length appears to be quite short. That's
you should select it from your select preset first.
Oh, you are right.
Okay.
There we go. That's a lot better. Thank you, Mark. See, that's why I need people with me. Okay, so the preset is there. So now we have this long body tube. So what you're going to want to do is, you see this plus here? You're going to want to drag it around. You see how it moves the component around in the body tube? You're going to want it so that half of the coupler, kind of like 3 inches, is probably the best. There. So you see how half the coupler is on the top of the body tube and the other half is on the bottom. The way that translates to real life, you can kind of imagine you have 2 separate pieces and this smaller coupler, and it's flush with the body tubes. It's like fitted perfectly. And so the way that's going to work is we're going to talk about building. You're going to glue one half of the body tube to the top, or one half of the coupler to the top body tube, and not glue the other side. This way you can slide the 2 sides together and the coupler will keep everything in place. And then once the ejection charge goes off that we were talking about last week, the body tube will be able to slide open, because the coupler will allow it to go out. So if you're doing halves, super duper important that you put the coupler in. And do use the preset. You're not gonna make your own couplers. So that's it for that. Now we go on to motor tube. Okay, before we move on, any questions about body tubes? I hope that everything is fairly simple when it comes to how to use Open Rocket. No. Yeah, I'll take that as a no. All right, let's move on. Motor tube. This is going to go on the bottom of your rocket here, and this is where, the motor goes in. So how does that work? Well, you're going to look for this inner component here for inner tube. You're going to click. Then we're going to look. The preset is LOC MMT-1.14. So we got preset. I don't have it here. So it was the, I already forgot LOC MMT. So we go click LOC MMT, this one. So we hit OK, select the preset. That is a long tube. What you're going to do is you're going to take length, and instead of 34, change to 3.5 inches. There you go. That looks more better. So just change that length down to 3.5 inches. That's what it shows on the slide. And then what you're gonna wanna do is you're gonna wanna take it and kind of add a little bit of overhang. So like 0. Maybe 25. Let me see what the slide says. I know you want to add some. Oh yeah, there you go, 0.25. The reason why you want to do this is because when you have the motor inside the tube, there's going to be a little part that kind of hangs out. So by doing this, you're going to position the motor tube just a little bit further down to help simulate the actual, rocket. So that's it. You just select the preset, change the length to 3.5, give it this little overhang here, and you're done with your motor tube. I trust that was fairly simple. Now for centering rings. So the centering rings go around the motor tube. So you have your motor tube, and then the centering rings attach to the outside of the motor tube, but to the inside of the body tube. And now keep your motor, centered. That's why they're called centering rings. So the way that you do that is you're going to hit up here to the inner tube, and then you're going to click here, centering ring. So you're going to click. And then for the centering ring, you're going to want to have, let's see here. We want to change, is there a preset here? I actually forget. No, it doesn't appear. Okay, so for the material, you're going to want to have plywood. There we go, plywood. The thickness is going to be 1/8 inch. There. So 1/8 inch. The outer diameter is going to be.
You put your centering ring inside your inner tube.
Oh, no wonder it's not working. I'm like, why is it not working? Put it in the body tube. My bad. There we go. It automatically measures it. Yeah, there's some things that I forget. I'm sorry. But anyways, so you can see that if you put it in the body tube and not in the motor tube, it will automatically measure how big the centering ring has to be to fit inside the rocket. So you can see here, outer diameter is 3, inner diameter is 1.21 inches. So that's good. So you're not going to want just one centering ring. You're going to want multiple to make sure that the motor tube is really secured. So the way that you can do that is we close, Control-C, and you just go Control-V, Control-V. So now we have 3 centering rings, but they're all on top of each other. That's not really what you want. You're going to want to take some of these centering rings and move them around, right? With this nice slider here, or you can even put specific inputs. You can say that's actually a really nice place for one of the centering rings. And then, oops, not that one. For the second centering ring, you can kind of put it a little bit closer like that. It's, your mic is hot. I'm going to mute you. Okay, cool. Anyways, you're going to want your center rings kind of like in this configuration. You can even take this bottom one and add just a little bit. What's the increment? I would honestly say minus 0.4 here. 0.25, but you get the idea. You can kind of play around. You see it, put the centering rings in this sort of configuration. That way the motor tube will be very secure. But it's very important that you leave a kind of larger gap here, because when we start designing the fins, I'm going to put the fin tabs I was talking about last week in that space. So that's how it's going to attach the rocket. But that's it for centering rings. You put down 3 or so. Make sure that it automatically fits into the rocket and kind of position them in this sort of shape. Alrighty, if nobody has questions for the centering rings, I'm going to move on to the next part, which is fins. Hey, look at that. Now that we're talking about fins. Alrighty, so here's how fin design works. This will be a bigger part of how you design your rocket. Everything so far has been very standardized, nose comes a certain way, body tube's a certain way, motor tube, centering rings, all of that is very, it's already rigid. It's already laid out for you. But chat, what's up? Where can I find the slides? They will be uploaded after the lecture, kind of like what we did last week. If you guys want the slides now, actually, Mark, if you don't mind releasing them, just so people can kind of follow along. Ooh, let's see. Okay, yeah. But Mark, if you don't mind, you can also put it up now just so people can follow along. But anyways, let's talk about fins. So fins are completely up to you. Okay, last week we kind of talked about fins and how you have to have the root cord longer than the tip cord, and all that stuff. It's gonna apply now. So the way that you put fins in is you're gonna look up here, and you can see 3 different options for fins. Let's go with trapezoidal first, kind of easier. So you click trapezoidal, and you look, oh wow, fins. So the way that this is going to work is there's a bunch of parameters I'm going to tell you about. Number of fins. This is how many fins your rocket has. You want 3 or 4. Don't go to 2, definitely not 2. Your rocket will not be stable. More than 4 is unnecessary. Also, don't do that. 4 is great for stability. 3 is more efficient, but can be less stable. Not that it's necessarily like a horrible thing, but it's just, you know, a little more stable with 4. Fin rotation. This doesn't matter. It just kind of rotates it. Like if you imagine your body too, fin rotation just kind of rotates it around like this. Don't worry about that. It doesn't help you. Fin cant. Do not touch that. What the fin cant does, I'll show you, is you see how it kind of makes it rotate like this? What's gonna happen when you cant your fins is your rocket is gonna have these sideways fins, and as it flies, it's just gonna start spinning. Please don't do that. If you cant your fins, you're not flying your rocket. So do not touch fin cant. We like to say you can't cant your fins. So yeah, bad, very bad. Root cord, very important. This is how big the bottom of your fin is. So you can see as I edit it, ooh, look, the bottom of the rocket's fins are increasing. So I would say that you kind of want it to be a little bit bigger. Like I like the 3.5 inches, something a little bit bigger. Yeah, so the root cord, you could play around with it. Have it slightly big. Though like 3 to 3.5-ish inches is nice. The tip cord, this is gonna edit the top, if you can see there. Make sure that your tip cord is never larger than your root cord. Otherwise your rocket will be in a very rough spot. But you can also edit this to your pleasing. And one thing that I want to point out, as I'm playing around with these parameters, notice how the stability is changing, right? As I do things, stability is changing. So as you're designing your fins, you're going to notice that, hey, when I do this, my stability is going down, but when I do this, it goes up, okay? And really depending on how you decide to design your fins, your stability is going to start shifting around. For the fin height, this is how, well, high the fins are. Make sure that they're not too crazy high. Otherwise, again, they'll be prone to breaking. And we'll not let you know if it's too high or not. And you'll notice, hey, look, my stability is actually at 2.56. So I'm actually a little too stable. Don't worry, that will be ruined once we put the motor in. But just understand that the height will increase your stability because, you know, bigger fins means that the center of pressure here, the CP, this little red one, is going to go further down and increase the distance. Sweep length. That is how far this distance from this corner to this corner is. If you guys remember from last week, if I edit it, ooh, it starts shifting around like this. And then sweep angle is the same thing as directly, you know, related to each other. It's really just 2 ways to define it. You either have this angle here, if you have like an imaginary line going up, and the angle from this line to that imaginary line, or the sweep length. For this, you don't really need to shift your fins up or down. You can shift them up a little bit if you so choose, but this isn't totally necessary. So does all this make sense? This is a lot to absorb, lots of little parameters that you can play around with. This is going to be the majority of your customization. Yes, it makes sense. Very cool. Okay, fin cross section, leave it square. Basically, if you have your fins, they'll be kind of square. Like if you hold them sideways, like if you sandwich your hands around your fin, it'll be square. The airfoil shape, you'd have to kind of form it into this weird airfoil, and it's really hard to do with 1/8 inch ply. So don't change this in essence. Leave it as square. That's what it'll do. For thickness, it's 1/8 inch because it is the same 1/8 inch plywood. And make sure that you do change the these parameters because that does, you know, edit the mass. For this, you can just put regular paint. It's a great assumption. You know, if you take like a can of spray paint, like what I did, you just go, you know, all over. It's going to be regular, maybe unfinished or something. But I think regular paint, if you do paint your rocket, it's a great assumption to make. Root fillets, don't worry about this. You're not going to use this. Okay, so moving on.
Change the component to plywood. You're on polycarbonate.
Oh. Accidentally clicked that. Thank you, Mark. All right, plywood, not polycarbonates. Alrighty. Now to fin tabs. Fin tabs are super important. You must have fin tabs, otherwise your fins are going to be in a rough spot. So if you look here, calculate automatically, pow, and it should have added fin tabs. Ooh, did it not have fin tabs? Oh man. Oh no, I think tab. Oh, okay. Sometimes OpenRocket can be a little dumb when trying to add fin tabs. Like right now, I'm having some issues. The way that you can fix that, if your centering rings are giving it trouble, you take the top one, kind of move it away, or even delete it. If you're to, actually, that's a good idea. Let me take the centering ring, copy it, take it out of the picture, and then try to do my fin tabs again. Let me see here. Why is it not adding my fin tabs? Because my tab height should be something like this. But it appears that OpenRocket does not really feel like it. Huh. Mark, do you have any ideas on this? I've never had this problem before. Or it just doesn't feel like calculating.
Yeah, also think like it's just OpenRocket being OpenRocket.
Yeah, sometimes OpenRocket doesn't feel like working. It's quite possible that I might need to just like kind of say if this is negative 2.5 or something.
Yeah, just like
Oh, it worked. It works. Yeah, it
Oh,
appears to have
awesome.
worked now. You see, I adjust something 0.01 inches. Yeah, sorry to interrupt you, Mark, but I think it might have worked.
It did work. It did work.
Oh no, it doesn't change the height. I'm not sure why.
Oh.
You know, because if the height is here, calculate automatically.
Yeah, just make sure like that your tab height is equal to like the outer diameter of your like body tube minus the outer diameter of your
Motor tube, yeah.
of motor tube. Yeah.
Yeah.
I'm going to release also like the bill of material, like with all the specifications of what we're having in the rocket. Actually, I'm gonna post it right now. You're gonna see there like all the measurements. We made it for you. It has both the imperial and the metric units. If you want to work with metric open rocket, I don't know. It, so yeah, I'm just gonna post it in a little bit.
Oh, that was a mistake. Yeah, it appears that it also does not want to bring my centering ring back, so I'm just gonna really quickly. Yeah, sorry about that little inconvenience, guys. This is actually one of the few times that OpenRocket really doesn't want to cooperate with me and calculate my fin tabs automatically, at least properly. But usually this works. Oh, okay, so this is a great example of when it doesn't work quite right. I have no clue why, but sometimes this happens. You would have to, kind of take the centering ring out of the picture. Actually, I wonder if that'll make it work. Yeah. But yeah, no, just you might have to wrestle with OpenRocket. It's an old program, so you got to give it some time. Anyways, but that's the gist of fin tabs. If you can make it work. If not, then as Mark said, outer diameter minus the size of the motor tube should get you there. Does anyone have questions for fins? Because I think that does the trapezoidal fin set quite nicely. Yeah. Not, then I'll just quickly go over the elliptical fins. You can use them. There's actually nothing wrong with using elliptical fins. You would just use this. Let me see here, actually. Let me just go ahead and really quickly go over elliptical. So you just put it, you can see that there's very similar parameters, number of fins, rotation, cants, don't do that, root chord, height, and you can play around with this. And then fin tabs, ooh, hold on. Let me make the root chord kind of like that. Fin tabs, calculate automatically. No, okay. Yeah, something's wrong with my rocket that OpenRocket doesn't like. Well, hopefully for you guys, this will work. And then freeform fins. This allows you to make any shape you want in a way. So if you were to do shape, you can see how there's these points here. You can kind of play around and kind of see how you can click and then add more points to the line. So I can do, this. Just keep in mind when you're doing your freeform fins, don't do that or this. one thing to keep in mind, like if you have these sharp edges here, that's probably gonna break. Not even joking. Like this fin, sure your stability might end up working. Don't do that. It's probably going to break. For all intents and purposes, it's probably best to stick to trapezoidal or elliptical fins and not doing that. So what I'm gonna do now is I'm just gonna really quickly just draft up just random fins, just to have some stability. 1.9, 2.13. Okay, cool. That looks nice. Then fin tabs doesn't feel like calculating right. Let me just add inch or so. Whatever. Actually, not quite whatever. I do want to have enough of a mass component on the bottom just to have accurate stability. Okay, cool. Alrighty, so that should explain most of what you need to know for fins. And keep in mind, you can customize your fins as you'd like. You don't need to do the shape. You can do, whatever shape comes to your heart as long as it makes sense to us. So yeah, let me change this out to apply and 1/8 inch. Okay, guys, if there's no questions for fins, then I will move on to the next part of the PowerPoint. Ooh, lots for fins. Do not catch your fins, fin tabs, rail buttons. Sure, let's do that. So what rail buttons are, you have your rocket, but you need it to be upright on the launch pad. So the way that it works is that there's going to be this long rail, and you're going to be able to put it onto that rail. And the way they put it on is with, well, rail buttons. So the way that you add the rail buttons is you might actually have to hit launch lugs. Yeah, it's the launch lug part, but we will have the specifications for your rail buttons. RG. Okay, so you go to the database, type in RG. I take, hey, look at that giant leap. Hit OK. Then you go to the preset. Nice. So the way that you're going to, the component is not at all. Should not be cardboard. Yeah, Mark. It should be something different. Polycarbonate.
Just use a random plastic like polystyrene.
Polystyrene, sure. Yeah, we'll have very detailed bill of materials later. This is just sort of a rough overview of how to do OpenRocket. But menus you close, and we're going to want 2 launch lugs. One is going to be on the top half of the rocket, and we're going to have the launch lug length. Radial position? No, I don't really need that. I need, oh, there it is. 0 degrees. This. You're going to want this kind of like higher up on the rocket. And what you're going to do is you're going to take this launch lug, copy it, and then paste it into this body tube. You're going to want this one kind of down by your fins. But actually what I'm doing now is bad because my fins are going to be intersecting with the rail buttons. So what I want to do is take this radial position and kind of put it with an offset. The way that you can tell if your rail buttons are okay is if you see view type, you can see a back view. So you can see that I have 2 rail buttons. The top one here is still in line, and I put it to 29-ish. So there you go, 25 degrees. So you can see from the back view, here are my fins, and here are my launch lugs. So you can see that the fins are no longer intersecting with the launch lugs. Before at 0 degrees, oops. You see how they're kind of intersecting with each other? That's bad. That is breaking laws of physics. So make sure that you give it some offset compared to the fins, just so it doesn't do that. And I would say actually put more like at least 35 or 40 degrees, just to really make sure that it'll fit on the rail. And we'll do that for the top one too. Also make sure that they're aligned here. Actually, for split body tubes, that being altitude and payload, don't worry about this. Basically, if your launch lugs are kind of misaligned, you can twist the body tube around. So don't worry about lining up. If you're altitude, or not altitude, lander, and you have a single body tube, make sure that it is aligned. We'll talk more about that during building, but really make sure that it's aligned, because if they are not aligned, they will never be. So yeah, that's it for the rail buttons. This one's a very simple part. Recovery. Okay, recovery is going to be a little more involved. So they were going to be sitting here for a while. All right, so for the recovery system, you need to add a few things. First, you're going to want to add the shock cord. Okay, so if you look here, you can go on this bottom body tube here. Oopsie. If you look here on the mass object, shock cord. Nice. Is there a preset component? Quarter flat elastic. Okay.
Okay.
Okay,
For
yeah.
elastic cord round, elastic cord flat 6 millimeters.
Elastic cord.
That one.
Flat 6 mil. Okay, so it's this one here. And then the packed length, what do we put as the packed length? Okay, well, the shock cord length should be 3 times the length of the body tube, at least. So if the body tube is 34 inches, let me just pull out my calculator real quick. 34 times 3 is 102 inches. This is a really good, sort of standard for how long your shock cord is going to be, because you need plenty of space so that when the ejection charge goes off, there's enough cord to absorb the force caused by that.
We're gonna give them 84 inches of elastic shock cord.
That's right. And then there's the
that's fine. It's less than like the 3 times like the length of body tube, but that's still good because it works like usually.
Sounds good. And then for pack's length, we're gonna want to increase, so you can see how the length kind of increases. What do we put down as the pack's length? Oops. Yeah. Well, what's important is that you're gonna want your shock cord, if you notice here, you're gonna want it more towards the bottom. Where the actual thing goes isn't as important. Something like 5.5 inches. Pack diameter can be a little bit bigger, as shown in the slide here. Actually, no, it's a little bit smaller. But in essence, what you're doing here is you're assuming that the majority of the elastic cord is going to be sitting on the bottom of the rocket. And the reason why you do that is because, well, when the rocket is standing upright and it is being launched, most of the cord is going to be, well, sitting on the bottom, right? If you are a altitude or a payload, you're going to have a bulkhead, which I'll put in later here, which you'll attach your shock cord to. So from here to here, having this 84-inch shock cord and a 17-inch, actually less than 17-inch space, most of it is staying down here. So it's good to assume that almost all of it sitting on the bottom. So that is it for the shock cord here, or at least I hope it is. Now let's talk about parachutes. This is going to be a little more involved. So first we're going to explain how we're going to do this. So last week I talked about dual deployment, where you're going to have, first your rocket is going to have the ejection charge go off. It's going to split apart, but the parachute will not be allowed to be opened by a chute release. It's going to hold the parachute closed, and then once it falls to 400 to 500 feet-ish, maybe even 300, depending on what we choose, that chute release will open up and allow the parachute to open. But we have to basically trick Open Rocket into believing that the dual deployment happens by having one actual parachute that deploys at 500 feet or so, and then having like a fake parachute that opens up later in the flight. So I'll explain how that works. So let's put in a parachute, okay? So for the parachute, it is down here. You are going to want to look, I think if we don't have a preset yet, then we'll give you guys a preset later. But, don't worry too much about this. We'll give you the details about the parachute later on. Let me just kind of make the, let's see, the pack diameter bigger, pack length bigger. Push it down here. You can even have it overlapping with the elastic cord a little bit. This is no big deal. Number of lines more like 8. Line length is 12 is fine. In essence, you're going to have this one parachute. And the super important part that you have to pay attention to, deploys at, not apogee, not this. You're going to have a specific altitude during descent. And you're going to put the altitude, let's put it at 400 feet for this simulation. So we have a parachute. It is real. It's going to deploy at 400 feet. Okay. And, depending on what we tell you guys, For this, it'll change how the parachute works. But those details will be released as you're designing the rocket. Someone's mic is on. Lucas, I'm gonna mute you. Okay. So this is important. Make sure that you do this. Now what we're gonna do is we're gonna put a second dummy parachute that I was talking about. So the way that you do it, parachute again, but this time diameter 0. You want 0, 0, 0. Actually, you can have a little bit, but you don't want this thing to really exist. And a part of that is you're going to go to override mass 0 grams. Okay, so it's going to be this parachute. It has no diameter. It has no mass. It basically doesn't exist. And you're going to want this to go off at apogee. So what's going? Oh, actually, no. You can do. No. Do it at apogee. Plus 9 seconds for the delay of the motor. So what does this mean? We're going to show you guys how to do simulations once we're done actually like kind of designing this rocket. At apogee, you're going to have your ejection charge kind of, actually, no, sorry. Just put this at 0 for now. You're going to have your ejection charge go off kind of at apogee, and your rocket is going to split. So this dummy parachute is telling open rocket, okay, the rocket has split apart, but there is no open parachute. So your rocket's going to tumble down quite fast. Then at 400 feet, as I put here, this parachute is going to go off, and it's the real parachute. And then open rocket will go, okay, real parachute going off at 400 feet. Once the rocket is simulated to have gotten there, it opens up, parachute goes, and your rocket lands safely. And I'll show you that once we pull up the simulation part. So that's why we need both dummy parachute and real parachute, and make sure that you put that there to get accurate simulations. Does that make sense? I know that it's weird. I know it's definitely weird, but as long as you follow the slides and you do everything right, you'll be okay. If not, then design a rocket for electronics as mass components. For electronics, it's pretty simple. All you really need to do, is you just go to mass component, just kind of this. You can even put mass type altimeter. For the masses, I can't remember them off the top of my head, but it's going to be a very small mass. How massive do you think, Mark? I forget from the bill of materials. I'm sorry, there's so much to remember for this stuff.
In the bill of materials, mass of, is that altimeter?
Yeah, just
okay. 0.35 ounces, or in metric, 9.9 grams.
Oh, 9.9 grams. Okay, 9.9 grams. Sick. All right, so 9.9 grams, and you'll get the bill of materials. So this will be quite simple. And then just stick this at the bottom, kind of with the shock cord here. Just because all these things will be attached to the shock cord and it'll all be sitting on the bottom of the rocket, you can easily assume it'll be sitting on the bottom. And then from there, you don't need to worry about this. The important part is that you have this mass component and that the mass is correct. Okay. And if there's any other electronic parts that we include, just make sure that you include them and kind of shove them on the bottom of the rocket. Okay, so that honestly encompasses the main mass components for electronics. So from there, we can move on to payload. If you plan on doing altitude, don't worry about this. If you plan on doing the payload or lander challenge, pay attention, please, because you will need to know this. So when you're doing your payload challenge, we'll do it for you guys first. You're going to want to do a couple of things. Your payload bay is going to be a coupler with mass inside. So you're going to do that for real. So what you're going to do, take a coupler, the preset that we gave you, and put it up plus some amount. Let's say here. So you're going to have your coupler, and inside you're going to have the egg. So what am I going to do? Well, I'm going to go into this tube coupler and add a mass component. And I can even put payload right there. So you're going to want to put the average mass of an egg. Let me Google that real quick. And this is a good assumption to make. What is the average mass of an egg? Mass of egg. 50 and 70 grams. Let's do the upper limit of 70 grams. And you're going to want the length. If you want, have your length and diameter to be the entire payload bay. And the reason why it's because not only do you have the egg inside, but you're going to have protective material all throughout. It could be packaging, peanuts, plastic straws. I don't know. You guys decide how you're going to do your payload bay. However you feel is best. And that's the important part for this. Now, one thing that I'm surprised hasn't been mentioned is bulkheads, because you're going to surround your payload bay with 2 bulkheads. So I'm just going to explain it to you guys now. How you do bulkheads is this. You press bulkhead, and it's going to automatically calculate here. Make sure that it is plywood, 1/8 inch. And then you can just kind of fit it ish. It's gonna take some fiddling. Oops. 5.7. No, that was bad. I need 6.1 inches. Kind of like that, 6.2 maybe, but you can see how it kind of fits on like that. Then you could take that bulkhead, Control-C, paste it back in, and then move it to the top. So you see how you have these 2 bulkheads kind of acting as like caps on your payload bay. 12.3 will work best. There you go. So there you go. That's a payload bay. That's what it looks like. And also for the bottom of the rocket, just really quick and on a tangent, you're going to want to put a bulkhead here. You're going to want to stick it kind of like on the bottom of this coupler here, because that's where you will attach your shock cord and all too onto this bulkhead. So I need 3.7. Nope. 14 inches. There we go. Something like this. So that's how you put your bulkheads in. And this is a payload bay for the payload challenge. Now, if you are a lander, things are going to work kind of differently. Let's go over that now. I'm going to have to make some adjustments. Actually, let me file new. Okay. Let me just really quickly make a super rough draft of this. I'm not going to include the fins and all just because we don't need to. But you'll imagine, you know, all the stuff that we have for the previous rocket, so the fins and all, will be there if you're in altitude. Or sorry, not altitude, a lander challenge. What I want to demonstrate is how you're going to be putting your lander inside of your rocket. So what's this going to look like? Well, you're still going to have a coupler as the base. And you're going to put it kind of up here. Make sure that there's enough space, by the way, for both payload and lander. I forgot to mention. Make sure that the shoulder comfortably fits above whatever you're putting in your rocket. If you don't, nothing will fit, and it will be sad. So make sure that you ensure that your shoulder has plenty of space before you hit this. And then inside of the tube coupler, you're going to have some mass. Let me make it 70 grams again, because that's what I decided to do. It's a payload. Make it flush. What we're going to do is you're going to put some more mass kind of on the bottom. And the way that you configure this is going to be kind of weird, but in essence, not only do you have the coupler, but you're going to have legs and stuff on the bottom of your lander. So you're going to want to make sure that you have that mass kind of accounted for, at least somewhat. Let's say I make a mass component, kind of like this, right? Like I assume that this area is like kind of my legs in a way, right? And then the mass, if I'm using wood, let's say it's another 60 grams, whatever. So this is going to be basically how big your lander is going to be. So what you're going to do is you're going to have your lander inside your rocket, but the ejection charge has to push the lander out of the rocket plus the nose cone. So the way that you're going to, before I go to that, you need to make sure that your lander stays towards the top of the rocket during flight. Reason being is because if you don't have a way to secure the lander in this particular spot up here, although it might be hard to fit in using your hand, once the motor goes off, that force will shove your lander right to the bottom of your rocket. And I've heard horror stories of that happening, and the rocket goes from stable to unstable on launch. And that is rough. And the reason why it goes unstable is if you take that giant mass component and shove it to the bottom of the rocket, suddenly your center of gravity just plummets down. And then suddenly you don't have enough stability to have your rocket fly straight. And that's from what I talked about last week with the whole, oh, if it's imbalanced, you generate a force, then it comes back. The magnitude of the moment is depending on the distance, and the magnitude of the aerodynamic force down here. Bring the distance down, the moment comes down, and now your rocket is not stable. So the way that you secure the lander onto a particular position is you actually take a centering ring. And the reason why we want a centering ring instead of a bulkhead is because you want like a hole where the gases from the ejection charge can push the lander and nose cone out, but still have that centering ring prevent the lander from going down. And the way that this centering ring will go is you'll have it kind of with a lesser thickness. Then, you know, you wouldn't use the normal like, oh, 0.1 or whatever. That's a little, oh, sorry, not the thickness.
Yeah.
It's inner diameter. My bad, guys. Inner diameter. You're going to want to point to, let me check out the back view just to see what this looks like. Back view. So you can see that. Oh, okay. Yeah. So the inner diameter, you can see how we want it. So we have this 2.2. So we want it to be somewhere around 2.7. So you have this kind of thin-ish ring, strong enough so that the legs can kind of sit on there and stay there during flight. If you want to be a little safer, 2.6 to 2.7 is good. But you can have your legs sit on that like really thin ring without it falling down during flight. This is crucial. If you do not have this, we will tell you, and you will have to change that. Because otherwise, as I said before, your lander is going to shoot straight down the rocket and will become unstable in a heartbeat. One thing I do want to point out, make sure that you have enough space down here for the lander to fit. My lander team miscalculated this, and this centering ring was way too high up, and we ended up having to basically cut the legs off of our lander. So it's more like a capsule more than a lander. So just make sure that you really carefully consider this part. Another method you could do, if you want to make it simpler, you can make a bulkhead and drill a bunch of like holes, just like using one of the drills at the TI lab, and just like have a lot so that the gases can push through. That's what my team did. It worked. But this is really easy if you do the thin centering ring, because you could just make the CAD model in SolidWorks that we show you next week and just have it laser cut for you without any more effort. So I think that is mostly it for payloads. Yes, this is it for payloads. And I explained the lander challenge too. Does everything make sense, guys? I know that I just did sort of a huge part of the crash course. Yeah, if there's no questions, I trust that you guys understand. Oh, chat just went off. Yep, cool. All righty, that's confirmation that I could move on. So now we go for motor configuration. So we have, I'm going to close this out. I hope nobody is sentimental towards this rocket because we don't need it anymore. Anyways, we have a motor tube down here, but there's no motor inside. So we need to put a motor in there. Otherwise, our rocket is going to be a bunch of cardboard, plywood, some cord, and parachutes and electronics. But not really a rocket. It's just going to just sit and do nothing. The motor is where the fun comes in. And so you're going to want to go ahead, hit the motor tube, inner tube. Actually, I can rename this up here. I forgot to mention motor tube, just to make it a little more clear. And you're going to want to go to motor. And this component is a motor mount. Click. Oh, there's motor overhang here. My bad. Anyways, this could also be another way to include a little bit of motor overhang. But if you do the tube like this, you'll be okay. Anyways, marking this as a motor mount. This will allow you to go ahead and put a motor inside of the motor tube. So after you click that, you close it and go to motors and configuration. You're going to notice motor tube is something that you can do. So you're going to want to do new configuration. You can see there's no motors. You're going to select a motor. And you can see this huge selection again. So many selections. You're going to want to look for a G17300. Let me see what the slide says.
G74.
Oh, G74. I'm in the high power category. I'm sorry, guys. G74, Aerotech. Yeah, I think that's the one.
Change
So,
ejection charge delay to 9.
oh, you're right, you're right. Ejection charge delay. Ooh, what the heck? I cannot see anything. Where's the ejection charge part? How did I forget? Oopsie. Oh, thank you. 9 seconds. So that is the ejection charge delay to 9. And I think that's it. I think we're okay. You select this, you press OK, and look, you see this little filling now? Suddenly, the motor is now in the motor tube. Congratulations, guys. You'll notice that my stability tanked because we have this giant mass component at the bottom of the rocket. But now you have your G74W-9 in the rocket. Checking stability, I'll talk about this. We like it to be between 2.0 and 2.5. If it's more than 2.5, you can say reduce the size of your fins, take off some mass, make your rocket a little more efficient. But my rocket right now, stability 1.18. Pretty bad, not gonna lie. So last week I talked about how to fix this. One of the ways, change your fins, make them a little bit bigger. So let's say I change the height to, ooh, look at that. If I change the height a little bit more, increase the root chord a bit, oops, the fin tabs automatically calculate. Yeah, there we go. It actually worked this time. I don't know. The fin tabs actually calculated correctly this time, guys. So I guess, oh no, it didn't calculate correctly, my bad. Hold on, I'm actually curious if I can make it work right. Go fin tabs. I think it worked. Yeah, no, the height is not 1, it's 9.45. Cool. Yeah, as we've said earlier, Open Rocket, kind of weird sometimes how it likes to function, but you can kind of wrestle with it a little bit and make it work. But anyways, as you guys can see, I've been increasing the total area of my fins, increase the tip chord a little bit. Let's see how sweep length does. See, look at that. Now these fins look a lot cooler. So you can see that by making my fins bigger, my stability increases because I'm pulling my center of pressure down, and that'll increase the distance between center of gravity and center of pressure. Also, you'll notice I have, oh, what's up?
Yeah, another way to increase the center to increase stability is adding more fins. So try.
Oh yeah, that's right. I only have
1.
3. So if I have 3 to 4, 2.46. Look at that. So yeah, adding the extra fin can really greatly increase the stability of a rocket. But I'll leave it to 3 for now because I want to show how to add mass to the nose to increase stability in a second. I want to emphasize apogee. What I was talking about earlier, look, we can actually see the predicted apogee of my rocket here that I've been designing. It's 1,007 feet. So as you, sort of play around your rocket, change the mass up here and do all this stuff, you'll see your apogee starting to change. So now my stability with my current rocket is 1.81, still a little bit bad. Here's the second way that you can improve it. If you go to your nose cone, actually click nose cone, you can put a mass component right here. Put it kind of here, and you can sort of play around. If I increase the mass, if you look, the stability is increasing over time. But you'll also notice that my apogee decreases. Of course, if you add more mass to your rocket, it's not going to fly as high. But that's not necessarily a bad thing, because if we set the altitude to 900 or 950 feet, you can increase your stability and kind of pull your apogee down to match our specifications. Mike, I'm going to mute you. Alrighty, cool. So that is the second way that you can go ahead and stabilize your rocket. And when you're doing this in real life, I'll explain this again in building, but basically you're going to put copper BBs or fishing weights on the top and then use epoxy to secure it on the nose cone. I'll give you more details about how to do that, for sure. But this is a very practical way and not that hard way to increase the stability of your rocket. Okay. So if there are no questions for stability, surface finish, don't worry about warning discontinuity. It shouldn't be so bad. Flight simulations. Okay, flight simulations is something that's really, really nice. So what does it do? If you look at this top here, flight simulations. The way that your simulations work is you can actually go ahead and kind of see how your rocket would perform if you were to fly in the real life. So how do we do that? Well, on flight simulations, we have our configuration here. Hit new simulation. So it's, okay, new simulation 2. just testing. So you're gonna have a bunch of little parameters. And I think there's some things that you can change. You don't really need to change these, like wind direction 90, average wind speed. You can basically change this like a best and worst case scenarios. Like let's say it were 10 miles per hour here, something like that. There's a lot of little details that you don't really need. Simulation options, I don't think you need that. What's next? What's next? What's next? I forget. I think you hit OK. Oh no, I'm doing this wrong. I want to see how we get to here. Oh, this bothers me. Oh no, I think we simulate and plot. Yes, we do. Okay, sorry. So simulate and plot, after you're done like actually making the simulation, then you can see a bunch of little parameters here. So what are you going to want to add? Let's see here. Motor ignition, motor burnout, apogee, recovery device deployment, and ground hit. I think we should have just about everything. Yeah. We want altitude, velocity, and vertical acceleration. I really think that is all. Oh, average wind speed. Oh, actually, I forgot that stuff. My bad. Average wind speed up to 15. The length of the rod is 36 as shown. You know, all these little details, very easy to find. Oh, I know why these two are flipped around. That's okay though. Okay, so after setting this up, simulate and plot. Ooh, yeah, there you go. All this is correct. So x-axis is time. That is correct. Cool. Let's plot this. Yes. So you hit plot and look at that. This is a graph. So this graph here kind of shows what your launch looks like. So you can see here altitude, vertical velocity, and vertical acceleration. So let's kind of look at this graph for a little in greater detail. I think if I do this, yeah. So what's going on? Well, here's the launch. You can see the acceleration just shoot right up as the motor is going off. And then, ooh, uh-oh. Oh, I'm stuck here. Oh, okay, this is fine. Oh, okay, cool. So you have your vertical acceleration just shoot right up as the motor is going off. And then once the motor starts to burn out, it's going to dip right down to the negatives. Because, of course, once you lose your motor, you're going to be accelerating downwards because of gravity, yeah? You'll notice the velocity goes up, and then it slowly comes down. And you'll notice the apogee. And at apogee, your dual deployment is going to go off. And you can see that it's going to kind of drift down like this. And then this point, the actual parachute is going to go off. And so you'll notice how the slope goes down. That's because the rocket kind of takes a little bit longer to drift down like this. So these graphs are really fun to look at. They can kind of give you some insights as to how your rocket is doing. And then you can see that this is ground hit. So that's really the gist behind the simulations part. And you know, you can do all sorts of things. You can do as many simulations as you want. And then we hit close, and hey, look, it's green because it worked. Yeah, so that's how you use simulations, and feel free to do as many as you want and kind of get an idea for how your rocket performs. And yeah, there you go. All right, you guys. I know it's a lot. Open Rocket can be very confusing at the start, but once you get the hang of it, it is such an easy program to use compared to, you know, anything else in the world, I feel. This is a reliable way to make your rockets for even your L1 certification. I use this program for L1 and I got it. So there's definitely something to that. Are there any closing questions? Since I've basically made a rocket, I've designed the rocket. Because if there are no questions, that's really it for the meeting. So yeah. Once, twice? No. Alrighty, guys. I appreciate you guys coming out. You know, learning about open. Oh, chat. No questions. Cool. I appreciate you guys coming out. Yeah, it's definitely a wild ride sometimes. You know, I get a little bit rusty with Open Rocket after all the time that I spent not using it. But we got there in the end. I appreciate Mark coming out and keeping me together and telling me when I did things wrong. And yeah, no, of course, guys, it's what I'm here for. If you guys have questions, message any of the officers. You can have fun kind of playing around with Open Rocket, you know, seeing how to do it. And make sure everybody fill out the form, the objective and team sign up form. please, please, please by next week so we can form teams so that you guys can, how many people per team? For altitude, you only really need 2 or 3. For payload, you want 3 or 4, and then for lander, you want 4. But it's gonna be like 2 to 4, but basically the harder the project, the more people you'll want. So that's the general rundown for people per team. And that's actually a great question. I should put that down in the form, but it's okay. I'll send a message to everybody, just specifying that. But yeah, so make sure they fill the form. And also make sure you pay your dues. If you haven't paid your dues, how many projects will you have the opportunity to do by this semester? You usually do 1. You would pick your challenge and you'll just do that challenge. But if you're asking how many projects in AIAA, whatever you have time for, you don't only have to work with us. You can also do some other projects. Any other questions, guys? These are all really good questions, by the way. I definitely should have been more clear on stuff like that. Okay, if you guys have questions or do you recommend solid? You don't really need to know much. We'll teach you how to use it. And also what we do, it's very simple. So you can, have no clue how to use SolidWorks, and we'll show you guys exactly what you need to know in order to, use SolidWorks for Rocket League. So how do we download SolidWorks? You go on the my.cecs.ucf.edu website. Yep, there you go. Oh, that was direct to me, but yeah, no, this website that's hopefully showing. And then you can go in there. There should be directions on the Google Drive that's hopefully sent out to everybody. And then make sure that you get the latest version, 21 to 22. That way everyone has the same version. And yeah, have downloaded. Yeah, get the latest one. Get the latest one, please. I tried to make an account and it asked me for an EMPN ID. So if you have questions, you should be able to email. Let me actually go to my.c. Oh, there you go. So one funny thing about the website, scroll down. You see this technical support? It doesn't look like you can scroll, but you can scroll, right? This is what I've been talking about. So scroll, you see this door access admin at ccs@ucf.edu. If you guys are having issues with your account, forgot your password, and it's not helping you, email that. They're really good about responding. They'll help you out. Yeah, of course. Because I don't manage this, so I don't know. But these people, whoever owns this email address, they know, so they'll help you out. Yeah, no, that's a big thing that I try to tell people, and I don't convey it very well. So I'm glad that I can show. Scroll down, you get this. It took me way too long to figure that out, by the way. I had to be told about that. All righty, I'll give one more chance. Any more questions about anything for Rocket League? And of course, guys, if you don't ask it now and you need help, don't worry. You'll be able to ask any of us on Discord, and we'll help you out, any of the officers. Yeah, I think we're good. I think we are good. It was a good meeting, guys. I appreciate everybody who came out, and I trust that everybody will be able to watch the video should they miss today's lecture. So yeah, I'll stop recording now. I'll see you guys next week in Rocket League.